Hi guys, Miss O'Connell here. So hopefully you had a nice long spring break. Some more updates about the AP exam are to come tomorrow. Today we're going to be talking about the version of work when we have a force that's instantaneous or a force that varies depending on the displacement. So we're going to review our definition of work in terms of an integral. Okay. So work we know is a change within a system that changes due to energy. Work is the integral of force as a function of displacement. Okay, in respect to displacement. Okay, so we're taking the integral of force versus displacement. Remember that when we integrate an equation for force in respect to time, we are talking about impulse, right? So if we're integrating f dt, that's the impulse, J. But if we're integrating a force that varies depending on displacement, we're looking at work. The work done on a system, okay, or done by the system. Okay, that means that the force changes depending on the displacement. Okay, so force is not constant. We use the integral relationship for work. If force is constant, we can use the F times D cosine of theta equation for work. So let's take a look at an example where our force would vary depending on displacement. Okay, so a wrestler applies a force over displacement during a match, represented by the function f of x equals 1/2 x squared plus 2x. Okay, so depending on its location, that force applied is going to vary. Calculate the amount of work done by the wrestler during the first 45 seconds if the opponent travels a displacement of 3 meters. Okay, so right off the bat here, right, that's meant to throw us off. First 45 seconds, doesn't matter how much time. Okay, work is dependent on force and displacement. Okay, a force that causes displacement. The force and the displacement must be parallel to each other. All right, so let's take a look at how we would solve this. So we have here our question, okay? So force as a function of displacement applied by the wrestler is as such. We know that work is the integral of force in respect to displacement from some initial to some final position. So based on the problem here, what's our initial and our final location? So hopefully by the word displacement, right, we can kind of assume here that delta x is 3 meters. So final minus initial would be 3 meters. So we say that the initial is 0 and the final would be 3 meters later. I gotta change this here. Put my upper and my lower bounds in the wrong place. No good. Okay, so from my lower to my upper bound, initial to final. So I'm gonna plug those in. So now my initial position and my lower limit will be 0. My upper will be 3. My equation, I'm going to plug that right in. Plug in f in terms of x right in here. So I'm going to integrate the quantity 1/2 x squared plus 2x dx from 0 to 3. So we're going to take this up really quick. X squared, we get 1/3 x cubed, a third times a half, we get a 6th x cubed plus x squared, 1/2 x squared times 2. The 2's will cancel, and we get x squared. We're going to plug in from 0 to 3. We know when we plug in 0 that each quantity will simplify to 0. So we're going to plug in that 3 value. So I have a 6 times 3 cubed plus 3 squared. That whole quantity minus 0. I'm going to run out of room here. And we get 13.5 joules. All right, so in classroom, there's also a set of homework problems I want you to give a try. Tomorrow we're going to have class during our regular scheduled period, and attending will give you lab points. You get points, a 10-point lab grade for attending. If you do not attend, you will get a 0. So you must attend again tomorrow during our scheduled time for a chat. Okay, so you're gonna give those homework problems a try. You can print them out, write them on lined paper, up to you. All right, so you know where to find me. Have a nice rest of your day, and I will see you guys tomorrow during our Google chat.